Hello guys, this is Jesse Precious. It's been a minute, and today we have a problem on WAEC from WAEC 1997, and it goes this way: two forces, 3 Newton and 4 Newton, act on a body in directions due north and due east, respectively. Calculate the equilibrium. Now, there are two things you have to know before we solve this problem. Number one is the method to solving the problem and what an equilibrium is. So firstly, the method I would like us to use to solve this problem is the parallelogram laws of vectors. This is not exactly a parallelogram problem, but the laws of parallelogram or the principles of parallelogram can be used to solve the problem. So firstly, let's know or let's acquaint ourselves with the laws of parallelogram. So parallelogram laws of vectors states that if two vectors acting at a point are represented in magnitude and direction by the two adjacent sides of a parallelogram drawn from that point, then their resultant is represented by the diagonal of the parallelogram passing through that point. I'm going to show you a pictorial representation of everything that was stated here. So let me take you back to the board. So we have here two vectors acting at a point due north, due north, and due east. And here we have 3 Newton, and here we have 4 Newton. And then they're all acting at a point here, point 0. And so we have here, we have here a resultant from that point. And then since we already know what our resultant, or now that we've acquainted ourselves with how or what the resultant is, we are going to now acquaint ourselves with what an equilibrium should be. So an equilibrium is a vector that is equal in magnitude but opposite in direction to the resultant of a system vector. So if it is equal in magnitude and opposite in direction, that would be something like this. And say we extend these vectors in directions both ways. So we have here, and then we have here. So here we have the equilibrium. We have the equilibrium. Now, let's say we reflect these sides on the plane. Then we have here 4 Newton here and 3 Newton here. Now to find, looking at it, if you notice, you find that there is a right angle triangle here, and to find the resultant you have to use the Pythagoras theorem. So initiating the Pythagoras theorem would be r square is equal to 3 raised to the power of 2 plus 4 raised to the power of 2, where we have here 9 plus 16, and then we have here equal to r square. So we have here 25 r square. Then we can square root both sides. Square root both sides. Square rooting both sides would mean here square root of r square and square root of 25, of which the r square cancels out the square, and then r is equal to the square root of 25, which is 5 Newton. So if equilibrium is meant to be equal in magnitude, that means resultant here being 5 Newton would also have an equilibrium being 5 Newton. Now that being said, we also have to find, one thing about vector is that you also have to find the specific direction, finding the direction. So if you were to find the direction, that means we would have here, say we call it theta, here would also be theta. The principles upon which that would be true is that opposite angles are equal. So taking that to cognizance, or taking note of that, that opposite angles are equal, the to find theta you have to engage the adjacent side and the opposite side, of which the trigonometric ratio for that would be tan theta. So tan theta is equal to opposite over adjacent, and in this case our opposite is 3 and our adjacent is 4. So 3 divided by 4 would give you tan theta. Tan theta is equal to 0.75. Then, since we are looking for the value of theta, tan has to cross over, and then we'd have here tan inverse. Theta equals the tan inverse of 0.75. So the tan inverse of 0.75 from my calculator is, wait a minute, would be 37 approximately. We have here 37. Back to the board. So tan inverse of 0.75 would be 37. So we have here to be 37 degrees, and here will be 37 degrees on the principles that opposite sides are equal. Now, one thing about bearing is that it has its references made with the vertical axis. So if here is 37 degrees, considering the fact that the axis for west and south are 90 degrees apart, if here was to be 37, that means here would be 57 degrees. Here will be 57 degrees. And then taking that to cognizance, we would have the vector's direction would be 5 Newton, then south 57 degrees west. And then to check if what we've solved is true, or the validity of our solving, sorry, not 57, it should be 53. My mistake. It should be 53 here, and here 53 as well. Please pardon. So we have here 53 degrees. So we have 5 Newton, 53 degrees southwest, 53 degrees southwest, or west of the south. And this becomes our final answer. So guys, tune in for more.